Hey guys, let's look at number 297, serialize and deserialize binary tree. I'll skip the explanations. It's very simple. It's like we get a binary tree like this, 1, 2, 3, 4, 5. We will serialize it to 1, 2, 3, null, null, 4, 5. And in a reverse way, if we get a string like this, we have to reconstruct the binary tree like this. So, okay, let's do it. So I think we have to remember that I think I'm not sure whether it is right or wrong, but if we do DFS for binary tree, it should be a stack. But if we show the BFS, DFS is stack, but BFS is queue. Okay, so for this case, obviously we're getting a BFS iteration. So we're going to first do this serialization by using a queue. Like we stack all the nodes of same level and we process them one by one. Okay, for one node we will push into the left node and the right node, and if it is, but for now we will suppose because for this kind of for trees that are not complete, we cannot decide whether 4 or 5 where it is. We have to append the null like this to be as a placeholder. Okay, so we use a empty array, result array, to store the temporary result, and at last we will join the result into a stringify the result. Okay, so we use a queue and we push the root in it. Okay, so yeah, the root may be null, but it doesn't matter. Okay, so we will say while the queue is not empty, what we were gonna do? Yeah, well, first we get the node out. We get queue shift. Okay, so we have to decide whether we have to check if whether node is null or not. If it is null, then we result just push null and it's done. And if it is not, we should result push node val. And then we need to push the queue to push result left, queue push result right. So if it's a leaf node, both of them are null, so we have a null, double null. So these will finish all those the tree traversal, and at the end we will just return JSON stringify result. Yeah, now the serialization is done. Now we try this deserialization. Our result is a little different from we had. Maybe it is not totally the same as the leetCode, because we have an extra null at the end. For 1, 2, 3, 4, 5, we have 1, 2, 3, null, 4, 5, null. So we have to trim the last nulls, right? Okay, so how can we do that? So while we just pop it, okay, but it's queue. In JavaScript, I think it's no problem. So while let's I equals q length minus 1 while q, why not? It's result, not q. While result is equals to null I minus equals 1. So, and then we will q splice. So we get splice I will stop at the first element that is not null. So we will splice I plus 1. It's not q, result. Okay, let's am I getting this right? I think so. So let's now do serialization. The first thing is that we get the data as string, so we need to make it const data. If data, we return null. Okay, and then array equals JSON string parse data, and if this data is empty, if it is empty or the first one is null, we return null. Yeah. And so if there is a root, when we do reconstruction, we will also use this q. So this q, we will wait a minute. We will create a root node, new tree node ARR0 const q equals root. Wow. Why we're using a q? Because for every time we need to know where the parent nodes are. Like, well, first we handle these kind of nodes, and then we handle these nodes. Without this queue, we cannot go back. Yeah, that's why we are using queue. We're handling with a breadth first search. Well, okay. While there is still elements in the queue, we get the node out. So for each node, we get the left node and the right node. For 1, we get 2, 3. For 2, we get 2 null, right? So we get const left value. Left val is array shift const right value shift. If left value, we only push. We here we need to do something. If the value are null, we just ignore them, right? So when the negative value, but the null is already as default value, so we don't need to handle it. So if it is not null, we will create the neft called new tree node left val and set it to the node left. And if right val is not null, we'll do the same, const right equals new tree node right val node right equals right. Okay, so but for these, when we are creating new nodes, like creating this 2 for 1 and 3 for 1, that means okay, these levels, the nodes in these levels are done, processed. We will process the next level, so we need to also queuing them. Let's push node left, push node right. In case for that 2, there are double null. We don't need to push anything because for that case, the 2 is dead. That like it is the branches are from 2 is already processed. So it's kind of like, okay, we first got the 1, okay, 2, 3. So we push 2, 3, and then we get 2 nulls, but we pop 2, so we're gonna be 3, 4, 5. Yeah, right. It's done. So the root is done, so we return root. I hope this will pass. Maybe there are some error. Oh yeah, it's always error, but it doesn't matter. What? Node result push node val. It says val of undefined. Null is undefined. Node is undefined. How could this be undefined? It's strange. Console node. It's strange. What does this mean? Val of undefined. Undefined. The next one is undefined. This is not result. It should be net node. I'm sorry. ARR is not defined, so I'm a little overexcited. It's ARR. Shit. It's shift, not shit. Time limit exceeded. What? It shouldn't be like this. Let's add some log. Wow, it's not q plus n here. It should be while the ARR length is there. My bad. Oh, there's an error. So we get this one, so we output this one, but we got extra undefined. Why? What is this undefined? Expected. Okay, first console log deserialize data. Deserialize 1, 2, 3, null, null, 4, 5. We'll get to the right one. And shift, push. We push node left. This should not be the axis, but maybe shift. My bad. Accepted. Okay, we will remove this console log and submit. Run answer. 1, 2. Console log d data and wow error. This problem that we omitted the last null, so we maybe there might be undefined. So and we just check null or undefined. Still wrong answer. Wrong answer. God. 0 is not should not. Oh shit. Oh shit. And left val should not be undefined. Submit. Shit, right. This, I think I cannot write it once and bug free. It's too difficult. But okay, it's accepted and it runs faster than 87%. Kind of good. Let's take a look at the solution. Depth first search DFS. The serialization of binary tree essentially to encode its value as more important. And more importantly, its structure. DFS, pre-order transversal transversal, is it right? Or it should be traversal? Transversal. Oh, should be transverse. I always say transverse. Oh, my bad. 1, 2, 3, no. 4, no. 5, no. Yeah. One can travel the tree time to each above backs, and it is well known that we have two general strategies to do: breadth first search, depth first search. The DFS strat can be further distinguished as pre-order, in-order, and post-order. Yeah, I remember this. In these tags, however, DF strategy is more adapted for our needs, since the linkage among the adjacent nodes is naturally encoded in order, which is rather helpful for the latter task of deserialization. Oh, they chose the DFS. I choose the BFS. Therefore, these algorithms, first of all, here's the definition of tree node. The pre-ordered DFS transversal. But traverse, why transverse? Transversal. Traverse. Actually, traversal, right? Traverse, I think. I always think it is traverse. I'm right. Okay, the pre-ordered DFS traverse follows recursively in order to root left subtree, right subtree. Example, let's serialize the following tree. Binary tree, 1, 2. Yeah, I think serialization is very simple. Serialize roots, else, yeah, it's simple. Now let's deserialize serialization string constructed. It's along the string, initializes the code value, and then calls itself to construct itself and writes the child nodes. So it's another way of writing it in the recursion. Deserialize linked list, deserialize data, recursively if it's null, remove, then left to right. Return root. It's very simple. Time complexity in both serialization and deserialize function. On space on. Both serialization function will keep the entire tree, either at the beginning or at the end. A solution with BF as a div strategy normally will have the same time and space complexity. And has was implemented above. The V, which means n times V, where V is the size of the value, which is called natural serialization. The NV complement here is encoding for values, can't be optimized further, but there's a way to reduce part, which is encoding of the tree structure. The number of unique binary tree structure can be constructed using n nodes, Cn, where Cn is Catalan number. Please refer to the article for more information. There are Cn possible structure configuration for a binary tree with the n nodes. So the largest index value that we might need to store is this. It means storing the index value could require up. I don't know what they are saying. Okay, we write this in the queue, but let's say we would try to use binary recursion. Let's do it again in a recursive way. Okay. Okay, const walk. I just use the walk node. If node equals null, then we say real result push null, right? Else, so walk node left, walk node right. And then we stringify the result. And when we deserialize data, we'll also say, oh, we will say this part is the same. And const walk, not walk, we just a build. Build, or how can I say build? Build index, okay. Build start. Const roots equals build 0 start. So start nodes should be because we use what's this order is a pre-order in order, right? This in order. So it should be 1 2 1 2 null 3 4 null. This. So if we build, we'll create the first node, const node equals new tree node. Start. It means AR start. This is the first node, right? node left equals build start +1. Oh, this is not right. So when I build from here, say this is node. Okay, this start 1. The next one is 2 because it should be good to the left node. So it's 2, and then null. Right? So we have to check the next one. If ARR start next one, and we return the node, is equal to null, build. We don't use this to start. Maybe we just need to treat const item equals ARR shift. We used to use this item. If ARR 0 is null, we don't care about it. So actually it is null, and we will check the again for the next one. So if it is not null, if it's like 3, then we will build it again, right? Yeah. So node left equals build No, we can just build. Yeah. If item is null, we return null. Node right equals build. Return node. I'm not sure whether it seems that it's working. It's not working. Okay, console log. First we deserialize. Oh, it's not stringify. God. Else, if it's not null, result push node val. It is null, then push null. If it's not, we push node val, and then we walk left and right. 1, 2. Console. I forgot to walk. Root. Property left is null. They cannot read property left are null. Root. Node rule. I have to return. God. Accepted. So the recursion here, you have to to take care that the first we got a complete binary tree format. It's 1 to like 1 2 null null 3 4 null null 5 null null. So every time we build, we get the first element. If it is null, then it's done. If it is not, then we create a new node and start building the left right, because each branch will stop at the when all the leaf nodes are built. So just to build safely, and we just return. Well, it's also very simple. Yeah, it's just fast. I think they just using the same. Whoa, it is a little faster. Cool. I need to write this one more time. Yeah, cool. So that's all for this problem. See you next time.